Welcome to this video on the anatomy of an anesthesia machine. My name is J. Thomas Murphy M.D., Professor of Anesthesiology at the University of Kentucky. I have no financial relationships with any companies. The goals and objectives of this podcast are to provide the anesthesia residents in our program with the most pertinent information regarding anesthesia machine and safety, to stimulate the learner to explore the history of anesthesia machines slightly, and to inform how a boatswain's whistle or Bosun's whistle is related to the practice of anesthesia. In our block 2 at this time, we have a number of educational offerings, including this podcast and part 2, as well as an upcoming podcast on the physics of the anesthesia machine by Dr. Hessel, and a flipped classroom with Dr. Rose. This schematic shows a generic two-gas anesthesia system from approximately 1987. I want you to note the presence of multiple check valves here, 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 and here, and regulators and pressure gauges in this simple anesthesia gas machine. This slide shows the gas flow diagram of a Draeger Apollo, the most commonly used anesthesia machine in our department. It is obviously less generic. You'll notice that the check valves are not labeled, nor is the auxiliary oxygen. It's check valve, check valve, check valve, check valve, check valve. This is the area of the auxiliary oxygen in the lower left corner. This slide is to show you a simplified schematic of a basic anesthesia machine with traditional components such as needle valves, glass tube flow tubes, and mechanical vaporizers. This is the GE Healthcare Aestiva 5, one of the machines in our department. This schematic does not show air, and that is because in days gone by, a third gas such as air was considered optional. Some three-gas machines used carbon dioxide. Heliox and oxygen is a third or fourth gas which can be fitted to an anesthesia machine as an option. Oxygen is the only essential gas. Nitrous oxide is considered to be an adjunct, however, used less frequently than in days gone by. There is a 9 to 10 minute video on the checkout of the Aestiva on YouTube, and this is the link. You cannot click on this link on this video. However, you could copy the link into a browser, or you could click on this link on our wiki page. Now, for the next few slides, we're going to discuss other anesthesia machines. There are other anesthesia machines out there. You'll have to learn how to use each one of them safely. The next few slides will cover some rather different anesthesia machines, and they may be different than any machine you have ever seen. Draeger and GE have the lion's share of the market, although there are others in the marketplace. Now, this is an anesthesia machine. It's a one-gas anesthesia machine. It may actually not be for humans. This web page shows some regular veterinary anesthesia machines. Animals need anesthesia too. This is a slide of 21st century anesthesia machines, perhaps not in in North America. However, these are a type of anesthesia machine. Obviously, you see there's no ventilators on these anesthesia machines, and they may be found in other parts of the world. This anesthesia machine, called a compact boils machine, is from Myanmar. These isoflurane vaporizers, both of which appear not to have key-specific fillers, are representative of the early days of these ventilators, these vaporizers. As you can see, one of them is labeled Surgivet, and obviously is a veterinarian product. This is a web page from the United Kingdom, and a used anesthesia machine by Omeda, GE Healthcare, of the Boyles apparatus type. And you can see this is a pretty simple cart. It's why many people refer to anesthesia machines as carts. And this machine has very basic, not much hidden features. You do notice it does have two gases and one vaporizer, perhaps two vaporizers. This is a photo of a classic Boyles gas machine, and the next few slides describe the features of this machine, which is sold in India. So the features of this Boyles apparatus include an oxygen failure warning device, a nitrous oxide cutoff system, and specifically when oxygen flow falls below 1.5 liters per minute, the alarm will be on, and it indicates that you have to close the nitrous oxide cylinder to stop the alarm. There is space for a ventilator. There is a McGill circuit complete with bag mount, and of course you all know what a McGill circuit is. Note that the only monitor which came attached to this anesthesia machine is a non-invasive blood pressure manual style up here. And this was a standard attachment on anesthesia machines as one of the main monitors in days gone by. This web page from the United Kingdom, 1996, has the same photograph, and it provides a reference for checking this machine, for example. Now, the primary reference in this podcast is chapter 29 from Miller's textbook, 8th edition. And I highly recommend that you read this chapter. There are a very large number of key points, and I've emphasized a few of them on the right-hand side of this slide. And the number one key point is to have a resuscitation bag and source of oxygen available. Believe it or not, this was not universal 20 years ago. There are some selected important key points that I've posted on this slide, and I think by and large they'll be addressed later in this presentation. However, if not, they are important key points. The secondary reference, which is accessible through Clinical Key, is this textbook titled Anesthesia Equipment, Principles and Applications, 2nd edition. And this PDF is easily available and can be printed out from the website if you have access to the website, and my understanding is that it is free. So, moving along, the basic components of the gas supply system includes the high pressure system, the intermediate pressure system, and the low pressure system. The high pressure system is confined to the cylinders and cylinder primary pressure regulators. The intermediate pressure system begins at the pressure regulated cylinder supply source at 45 pounds per square inch and includes the pipeline sources of 50 to 55 pounds per square inch and extends to the flow control valves. The low pressure system extends from the flow control valves to the common gas outlet. Now, what is a check valve? I showed you the location of check valves on anesthesia machines. Not all anesthesia machines have check valves in the same places. A check valve is a flat valve in the connectors as shown here, and when positive pressure is applied against the direction of flow, a check valve prevents backflow. Anesthesia machines have check valves, and this is the same diagram again showing check valve here, check valve here, check valve here, check valve here, a check valve here or internal to the vaporizer, and this is what keeps gas flowing in the correct direction. Now, an important concept to gain here is that the cylinder valve on the back of the machine must be closed when not in use. And this is a direct copy, cut and paste from the 7th edition of Miller's textbook, and it very clearly explains that the gas supply cylinder should be turned off when not in use, except during the preoperative machine checkout. It further explains that if the cylinder supply valves are left on, the reserve cylinder supply can be silently depleted whenever the pressure inside the machine decreases to a value lower than the regulated cylinder pressure. And this can occur in some machines during oxygen flush, etc., etc. If the cylinders are left on, they will eventually become depleted, and no reserve supply may be available if a pipeline failure occurs. From the APSF and found on the University of Florida Virtual Anesthesia Machine website, there are teaching points, learning objectives, and this website is very worthwhile your accessing and registering. This question, in my opinion, depends on a properly functioning check valve on the oxygen pipeline. The question is, during a case, the oxygen pipeline supply has failed. You open the oxygen cylinder and continue the case. In addition to oxygen from the cylinder flowing into the anesthesia machine, will it also flow retrograde into the oxygen pipeline and prematurely exhaust the O2 cylinder? In this case, the answer is no, and that is dependent on a check valve. And the explanation is that O2 pipelines are fitted with a check valve that prevent retrograde flow of oxygen to the oxygen pipeline. This list of high pressure system learning objectives is asking a similar question or an identical question. If the O2 pipeline is connected and pressurized and the O2 cylinder is opened, will an anesthesia machine be supplied with oxygen from the pipeline or the cylinder? And I believe that the same question is answered here, except that it brings the question of whether or not the gas supplied by the oxygen pipeline may not be oxygen. So if the primary source is the pipeline, and if you feel that the pipeline may be contaminated or not oxygen, what you must do is disconnect the oxygen pipeline from the anesthesia machine, and that is outlined in this learning objective at the bottom of the slide. The O2 pipeline has to be disconnected or at a supply pressure lower than the downregulated cylinder pressure, normally 40 pounds per square inch, for oxygen to flow from an open cylinder. So that is how the check valves and two sources of oxygen for an anesthesia machine work. And this is again the diagram of a check valve, which is designed to prevent gas loss from an oxygen cylinder on the back of the machine. So the Apollo User's Manual addresses this, and in the checkout of the machine, you're expected to check the pipeline supply LEDs on the front panel. If the pressure is less than 39 pounds per square inch, the LEDs will not light up. And if the cylinder valves, if the oxygen cylinder valves or the relevant cylinder valves are open, it is possible that the gas will be depleted. So, in conclusion, you must close the cylinder valves whenever the pipeline gas supply is sufficient. Same slide, just reiterating that gas may flow from an open cylinder when there are pipeline pressure dips. Now, we're going to move on to a safety feature of the anesthesia machine: oxygen supply pressure failure safety devices. This slide from the Mushin Museum describes a Bosun whistle, and it comes from the 1950s and was standard oxygen failure device on anesthesia machines in the 60s, 70s, 80s, and it was designed such that it was powered by declining gas pressure, so that once the oxygen failed, a whistle would be sounded, but it would not persist, it would not last. Therefore, they added a battery-powered alarm light, which was, on the back of the machine. So this is not a perfect system. However, it did provide a whistle, a sound, some sort of way of the end user picking up the fact that the oxygen supply from the wall had failed or had ceased flowing. This is an up-close picture of the Bosun whistle. Now, here's a few questions for later on. Who or what or was or is Mushin, and who or what or is Bosun? These are interesting anesthetic concepts, in my opinion. The first slide, this slide is from the Omeda or GE, and shows that the approach here is to use a pressure sensor set-off, which closes the oxygen supply when the pressure falls below 20 pounds per square inch. So if this shuts off the nitrous flow here completely, so it's all or none. The Draeger system is proportional, and as the oxygen supply falls, the supply of nitrous oxide is reduced. So the main differences between these two manufacturers are the fact that Omeda is threshold or all or nothing, and that Draeger is variable flow in its oxygen supply cutoff or proportioning system. Flow meter assemblies. All the machines in our department have glass tubes, and the flow meter is called a Thorpe tube. It's made of glass, has a mobile float indicating the amount of flow. Opening the needle valve allows flow through the tube. Flow may be laminar or turbulent. When laminar, viscosity does influence flow rate. When it's turbulent, density is the main physical characteristic of the gas, and and which influences flow rate. So accuracy can be affected by laminar or turbulent flow. Flow meter assemblies have problems. They have leaks, they have O-rings, they have the glass could be broken. There's the oxygen leak from a flow tube can result in a hypoxic mixture. Therefore, this is why it is essential to have an oxygen analyzer downstream of the flow meters. These flow meters are designed to work accurately in the vertical position. It does bring into question how accurate the flow is when a cylinder is placed horizontally in the patient bed. And overall, the cylinders with flow meters should not be placed in horizontal or angled positions. There are other safety features associated with flow meters, and they include fluted oxygen knobs, color coding, knobs which are recessed or protected, and such that inadvertent alterations in setting is avoided. If a single gas has two flow tubes, they are arranged in series and controlled by one flow control valve. Some newer workstations have electronic flow meters, which could possibly eliminate leaks associated with glass tubes. One of the main reasons we selected the Apollo is that it has traditional flow tubes, and even in the case of a failure of the machine, there is a small glass flow tube and a float that tells you the total gas flow. Yet more safety features associated with flow meter assemblies include flow tubes that have the name of the gas etched on them. The flow tubes may be pin indexed and can only be assembled in one way. They may come as a single unit so as to avoid errors in repair. Now, moving forward, we are going to review oxygen nitrous oxide proportioning systems and patient safety. This slide shows the Omeda Link 25 proportion limiting control system. This has been in use for several decades and is a combination of mechanical bicycle chain-like system, which is designed to limit the dose of nitrous oxide with the minimum oxygen of 25% in if working properly. Alternatively, Draeger has a different system for preventing hypoxic mixtures, and this oxygen ratio monitor controller shown on this Draeger slide is designed to cut off the flow of nitrous oxide at flows under 200 mils a minute. And it is important to know that this oxygen ratio controller is not active when air is selected as a carrier gas, and 100% air can be metered throughout the entire range. There are limitations of proportioning systems. The wrong supply gas could be in the gas line. There could be defective pneumatics. There could be leaks downstream. An inert gas could be administered, and it would further dilute the oxygen concentration. The use of relatively weak agents like Desflurane, requiring 6, 7, 8, 9, 10% of the inspired mixture will dilute the oxygen concentration. Most importantly, though, I feel that that inadequate end-user knowledge is a limitation of proportioning systems. Specifically, air is 20% oxygen. Therefore, 1,000 mils of air has less oxygen than the average person's oxygen consumption. When you use nitrous oxide and oxygen, it is possible to deliver 750 mils of oxygen, nitrous oxide or so, and 250 mils of oxygen, and that will result in an FiO2 of less than 25% if, as the case progresses, because while the oxygen consumption is fairly fixed, the nitrous oxide uptake becomes less and less over time. If air and oxygen are used in combination, it is possible to and result with a lower FiO2 than desired. The point of this slide is just to emphasize the fact that this oxygen controller system is not active when air is the carrier gas. This is a cut and paste from Miller's 8th edition showing both kinds of oxygen proportioning systems, and essentially one thing I did learn in this review was that the 2-to-1 ratio of the mechanical linkage results in a 3-to-1 ratio of nitrous oxide to oxygen because of a difference in the taper of the nitrous oxide valve needle, and that's expressed here, and is an interesting physical aspect of the anesthesia machine. You can have an FiO2 of more than 25% flowing through the vaporizers, but the patient FiO2 ends up being less than 25%. And this has to do with the end user recognizing the fact that that there is uptake of nitrous oxide, which is variable, and sometimes increasing amounts of oxygen consumption for the patient. So now that we've addressed some of these aspects of this safety features, we'll move along to the low pressure leak test. Now, the GE Datex Omega machine, many of them have a check valve which requires the performance of a negative pressure test, not an oxygen flush test. In this test, a suction bulb is attached to the common gas outlet. This is a suction bulb. This is shown very clearly in the video link that is referred to earlier in this podcast. So a suction bulb will remain sucked flat if there are no leaks. If there is a leak here, this suction bulb will not maintain the negative pressure. So this is a test which I did teach people to do at one time when we had more Aestiva machines. Our department does not have a suction bulb in every machine. Some departments do. It's considered part of their daily check for an Aestiva or similar machine. This slide shows the wrong way to check an oxygen flush valve, and if you pressure test the system, that check valve prevents the positive pressure from going back to the vulnerable area or to where the leak is, and you do not pick up the fact that there is a leak in the system. The Dragger Apollo does an automated low pressure leak test, and this diagram shows the components of the circuit which are tested by a automated test, and it is performed with sub-atmospheric pressure. At some time you should probably practice or test an Apollo machine and breathe through the circuit with an inadequate amount of flow, and see what happens when you get to a negative pressure. There is a valve in the machine which should open up and entrain room air. So the Apollo determines the current leakage of the breathing system and breathing hoses, and it will pass the test if there's less than 150 mils a minute. There are a number of locations where leaks may be occurring, and the machine does not tell you where the leak is, so you have to explore that yourself, and they include possible causes include the absorber not being screwed in tightly, the APL being damaged, the bag itself, or the breathing hoses, or the flexible arm being damaged, or the a sealing ring being soiled or damaged, disconnections of various sample lines, and it goes on. There's a number of screws and such that if they were not tight, a leak could be presented. So from the Dragger manual, there's a screen capture showing some suggestions for determining where the leak is, and if you isolate specific items and perform the leak test, you will be able to detect most likely whether or not the sample line is the site of the leak, or whether or not it is the breathing hose, and or if it is the vaporizer. Now, by my clock, this podcast has been going on for a little bit more than half an hour, and you have another video that's of about 10 minutes duration for you to watch. So yeah, it's time to lighten it up a little bit, and we'll address the question, who or what is or was a Mushin? And Professor W.W. Mushin was the chief of anesthesia at the University of Wales in Cardiff, and is a renowned pioneer of anesthesia, having died in 1993. I bring this to your attention because diagrams from his textbooks from 1963 are still being used in our textbooks today. And on this website, you have already been exposed to the Bosun's whistle, and this Bosun's whistle, or Bosun's pipe, is a musical instrument which perhaps may play like this, and it is used to give commands on ships, and this is what the oxygen failure alarm system sounded like in days gone by, when the primary oxygen alarm was the Bosun's whistle. But just like that short sample, it didn't go on for a long time, and you had to be ever listening for oxygen failure. A slightly more modern oxygen failure device was the Ritchie whistle, and it was brought into manufacture and use in the 1980s. And as anesthesia machines became more complicated, more complex, such as the narcomeds, by Draeger and the various lines of um, uh, anesthesia machines by GE, Omeda, etc. These add-ons or these Boyles apparatus machines were had their own oxygen supply failures. So when you do your anesthesia machine check every day, you should hear the sound of an oxygen failure um, being detected by the machine when you unplug the supply from the wall with the cylinder turned off, for example. So I refer you to this website where I located these photographs, and there are not many items to browse on this website. However, it is kind of interesting when you're looking for historical items in the field of anesthesia. This is the end of this podcast, part 2 to follow. Thanks very much.